Welcome! By the end of this lesson, you will be able to predict exactly where a thrown object will land, how long it stays in the air, and how fast it travels when it hits the ground. Projectile motion is the ultimate test of your kinematics toolkit. It is a guaranteed high-mark question in Paper 2 and forms the mechanical foundation for electric fields and particle physics in Paper 4. Before we calculate anything, we need to establish the core principle. A projectile is any object moving freely under gravity with air resistance ignored. The single most important fact, the key that unlocks every exam question, is that horizontal and vertical motions are completely independent. Once an object is launched, gravity pulls it downward. Gravity does not pull sideways. Therefore, the horizontal velocity remains perfectly constant, while the vertical motion accelerates under gravity. They do not affect each other. Let us test your intuition on this. A steel ball is fired horizontally at 50 meters per second from a height of 2 meters. At the exact same instant, an identical ball is dropped from rest from the same height. Which ball hits the ground first? Pause the video, think about it, and decide. They hit the ground at the exact same time. Both balls have the same initial vertical velocity of 0 and the same vertical downward acceleration of 9.81. Because horizontal and vertical motions are independent, the fired ball's massive horizontal speed does not keep it in the air 1 fraction of a second longer. Section 2. Resolving the launch velocity. Unless a projectile is launched perfectly horizontally or perfectly vertically, its initial velocity is at an angle to the horizontal. Before you can use the independence principle, you must split this launch velocity into its components. Using basic right-angle trigonometry on the velocity vector triangle, the horizontal initial velocity is u cos theta, and the vertical initial velocity is u sin theta. But beware the classic examiner trap. A javelin is thrown at 28 meters per second at an angle of 35 degrees to the vertical. What is its initial horizontal velocity? Read carefully, pause, and calculate. It is 16.1 meters per second. Because the angle is given to the vertical, not the horizontal component is now the side opposite the angle. Therefore, you must use sine, not cosine. Always draw a quick triangle in the exam to avoid this trap.
Section 3. The two-column method. Because the two motions are independent, you must never mix horizontal numbers with vertical numbers. The A* method is to draw a line down your page and create two columns. In the horizontal column, acceleration is 0, so velocity is constant. In the vertical column, acceleration is negative 9.81 and full suvat applies. The single quantity that connects these two columns is time. The projectile is moving horizontally for exactly the same amount of time that it is moving vertically. Let us see this in action. First, resolve the initial velocity. The horizontal component is 20 cos 30, which is 17.32. The vertical component is 20 sin 30, which is exactly 10. Next, set up the vertical column. Take upward as positive. Because the ball lands back on level ground, its overall vertical displacement is 0. Acceleration is negative 9.81. Use the vertical suvat equation for displacement to find the time of flight. Factoring out t gives a time of 2.04 seconds. Finally, carry that time across to the horizontal column. Horizontal velocity is constant, so the range is simply the horizontal speed multiplied by the time of flight, giving 35.3 meters.
Section 4. Maximum height and the parabolic trajectory. The path of a projectile in the absence of air resistance is always a parabola. This shape occurs because horizontal displacement increases linearly with time, while vertical displacement changes with the square of time. At the very peak of this parabolic trajectory, the projectile stops rising and is about to start falling. Therefore, at maximum height, the vertical velocity is exactly 0. This is your mathematical key to finding the maximum height in any exam question.
Let us check your understanding of this peak. True or false? At its maximum height, the velocity of a projectile is 0. Pause and think. It is false. At maximum height, only the vertical component of velocity is 0. The horizontal component of velocity remains constant throughout the entire flight. Therefore, the projectile is still moving horizontally at the peak. Claiming the total velocity is 0 here is a highly common mark loser. Section 5. Recombining components for landing velocity. When a question asks for the velocity of the projectile as it hits the ground, it is asking for the resultant vector. Giving just the horizontal or vertical component scores 0. You must recombine them using Pythagoras for the magnitude and trigonometry for the angle. Let us finish with a horizontal launch from a cliff. Step 1. The horizontal component. Because horizontal acceleration is 0, this never changes. It remains 15 meters per second. Step 2. The vertical component. Taking downward as positive, use SUVAT with the time of flight to find the final downward speed of 29.7 meters per second. Step 3. Recombine them. Use Pythagoras with the two components to find the resultant magnitude, which is 33.3 meters per second. Step 4. The direction. Use inverse tan of the vertical over the horizontal to find the angle, which is 63.2 degrees below the horizontal. Let's review your A-star checklist. You are now ready to tackle projectile questions. Remember to always draw a quick sketch and resolve your launch velocity first. Set up 2 distinct columns and use time as your only bridge. At maximum height, set vertical velocity to 0, and when asked for final velocity, always recombine your components to give both a magnitude and an angle.